week 9, and we are getting close toward the end. Still, we are dealing with the topic of the bending. So bending, it starts with you finding a member subjected to um, a certain load of type, which is the structural member resists the external loads by the action of the bending. So when it bends, the curvature of the beam changes, and this you can identify by visualizing the deformed state of the structure when the structure is made of a very soft material. All right, so as we discussed last week, there is a relationship between three important um, variables of the beam member. So these three variables are starting with the most important one are the external loads. And we remember that the external loads could be either point load or distributed load. So this is an example of a point load, but at the same time, we could have something distributed. So let me just, for the sake of example, and this is not applied to this problem, but here, that distributed load, we call this W of X. So what X implies is the distributed load changes axially or longitudinally. And so this is the first variable. The second one is V of X. All right, so this is the second one. And the third one is M of X. And also there is something called N of X, which is of less importance. So sometimes you might be asked to derive N of X with X, but this is not very important in this structure. I mean, most of the cases, a beam critical situation is dictated either by the shear force or by bending moment. Normal force is very unusual to be a critical part. All right, so like I mentioned, there is a relationship between 1, 2, 3. So let me summarize for you the relationship between these forces. I know that the variation of shear force with respect to the axis, that is equal to W of X. Also, I know that the variation of bending moment with respect to the X, that is equal to V of X. So it means if I want to go from this graph upward, so if I have been provided by M and I want to find V, what I do is the differentiation. And if I want to go in the downward direction, such as I have W of X and I want to find V of X or M of X, what I do is integration. So this is differentiation, integration. Differentiation to go upward, integration to come downward. All right, so we went through a good number of examples last week, and we keep doing the same thing now. So in that sense, what happens if I do have point load rather than W of X? If I do have point load, who can tell me what is the difference? I mean, point load could be either a shear force or a point bending moment. So the bending moment is regarded as um, point rotation. This is a point load, this is a distributed load. So here I mentioned the relationship, the derivative and antiderivative relationship between 1, 2, 3. So who can tell me what happens if we have the point load? Anyone? Ben is quite correct. Having a point load makes the graph to be discontinuous. And if I have a point load in the shear, like 5 kilonewton, That is the discontinuity you see here, right? If that was purely W of X, you didn't have this discontinuity here. But now, because of that discontinuity, there is a jump. So this is pushing down. There is a jump from 2.5 to minus 2.5. So how much jump is there? The jump is 5 kilonewton. So if I did have a point bending moment, the discontinuity would have been visible on the third diagram, not in the second diagram. So this is not the case here. In this case, we have all the bending moment continuous, but if that was the case to have a point bending rotation somewhere along the beam, the result becomes would have been visible on the third diagram. So you would have had a discontinuous moment X plot. All right. So I think that that's a good summary of what we did so far. And so this is a typical example. I mean, how you describe the beam in the first in the top graph. So what would you say about the W? What is the W in the top free body diagram? Ivan, what is the W in the top diagram? In the first zone? Yes, yes. No, no, no. I am talking, Ivan, I'm talking about the W of X. W of X, how do you describe it in the top free body diagram, Ivan? Yes, correct. That is zero. All right. Still, if that is zero, you can't integrate zero. So the integral of the zero is constant because from constant, if you derivate, it becomes zero. All right. So reverse anti-derivative of the zero is a constant. So thank you, Ben. Thank you, Ivan. Both correct. So in this case, that explains why the shear doesn't change in the first zone. In the first zone, we whatever shear we have is 2.5 at point A. That remains constant between A and B. And why is that? Because W of X in the first zone is zero. All right. Please let me know if everyone followed that um, clarification. If you didn't, feel free to change your status and then I repeat. Thank you, Ben, Yvonne, Lachlan. What about everyone else? I need to have at least two more feedbacks before we proceed. Two more feedbacks. Any feedback, whether you are confused, whether you, yeah. All right. Let's move on. Uh, I'm here to help in case if you need me, just let me know. All right. Now, this is a more complex situation. I mean, that is not um, too bad. Let's get this solved together in the class. So I think that would make a good summary for what we are now. So here I have been provided with a beam structure and my beam is subjected to a distributed load. All right. So with that distributed load, what I have to do is first I need to find out the reactions. So how did I find the reactions? 18 kilonewton and 9 kilonewton. How did I find it? So the answer is I have to replace first I have to find the reactions, and first step is find reactions. So for this, the first step is replace distributed with point cloud or resultant. How do I do that? I need to find the area of the triangle. So area of the triangle, that is equal to minus 6 times 9 divided by 2, correct? That's the area of the triangle, which is minus 27, right? Minus 27, that means the resultant force is acting downward. And now that I replace the distributed force with a one resultant load, I can solve this free body diagram to find out the reactions. And so if we solve the free body diagram, we find the reactions being the left-hand side. Let me call this A. This one I call this point A. This one I call point B. So we find both reactions. So how many zones are here? Is this one zone, two zone? How many zones should be defined here? Yes, that is correct. Thank you, Lachlan. There is only one zone here, and that is between A and B. So that is zone number one. And that is X changing between XA and XB. So if I take my coordinate system starting at A, that X would change between 0 to 9. And for that zone, I need to write an expression for W of X. So how do I define W of X? Jaden, can you tell me how Wx can be identified? Ashwin, Tapiwa, just feel free to use your microphone if that is more comfortable. Khan, Jack White, Gabriel, how do we find, how do we identify the expression for W of X? Is this a line, is this a quadratic, or is this a cubic? How do you describe W of X? Lighting, how do you describe the expression for W of X? Is this a line or quadratic or cubic? Yes, thank you, Lighting. That's a line. And here I write a generic equation for a line that is AX plus B. Thank you, Lighting. And now, how do I find A and B? So now I need to find A, I need to find B. That is what we call identification of the W of X. This is the most critical step for solving, for graphing the bending moment and shear force. So you have to identify W of X. So please listen very carefully. The way we identify A and B is by point values. So I know that W at point A, that is W of A, which is W at X equal to 0, is equal to 0, right? So let's plug that into the expression. That is A times 0 plus B. And if I solve here, B becomes 0. So that is equal to 0. Now, how do I find B? I know that W at point B, that is W at X equal to 9, is equal to what? Is this equal to 6 or minus 6? Khan, is this 6 or minus 6? Yeah.
6, sir. 6.
No, this is minus 6, Khan. Why is minus? because it's pushing down, isn't it? Correct? Do you agree, Khan?
Yeah, yeah, yeah. I see.
Okay. So this is I want everyone to pay attention. For convenience, we put the distributed load at the top. That could be confusing, but you shouldn't forget that this is a negative distributed load, and therefore here I put minus 6. Thank you, Han, for that. And now let's plug that into the equation. So that is A times 9 plus B. B is 0. So from here, I can identify A, can't I? So A is minus 6 divided by 9. So if I divide that by 3, that is minus 2 thirds, correct? So now I have this minus 2 thirds. All right, so we managed to get the very important step, which is to identify W of X. Why W of X is so important? Because that is a starting point, right? So the next step is I'm going to use equation number one. That is equation number one. That is the derivative of the shear force with respect to the x is equal to W of x, which is equal to minus 2 thirds x. And now how do I solve that? That is by integration. So this is the integral of dv is equal to integral of minus 2 thirds x dx. Everyone follows that? So what about the bond of integration? I want to integrate that between x equal to 0 here to x equal to x. So I want a typical point between A and B. A typical point between A and B is point x, right? So 0 to x. So now if you remember from how did we do integration in calculus, that is the upper one is v of x, the lower one is v of 0. And the right hand side is integral of 2 thirds x is minus 2 divided by 6 x squared between x to 0, right? And that can be simplified. This is equal to minus 1 third x squared. And at this bound, this is that minus 0, right? So let's go back to the left hand side of the equation. What is v of 0? Who can tell me what is the v of 0? Jack White, what is v of 0? Jack White, are you there? Hello, Jack. The entire class is waiting for you. What is confusing about it? What is the shear force at point A? Gabriel, what is shear force at A? Okay, that is 9 kilonewton. Thank you, Jack, for that. So I put this one at 9. That makes V of x minus 9. That is equal to minus 1 third x squared. And from here, I find an expression for V of x, which is minus x squared divided by 3 plus 9. All right. Now we have an expression for V of x, and we can plot that. So this quadratic curve, is this a reverse curve or this is a upside uh, curve? So because this is negative, we know if the coefficient of the cubic is, so that is when you have a smaller than 0, and if that a is positive, so your quadratic would be like that. All right. So this is the case when you have a reverse curve. So with this reverse curve, and now I should be able to okay, start from 9, that is 0.9 here. And because this is reverse, we have to do it upside down. Okay, and I do need to find the final value. So these are the endpoints. I know that The starting point is 9. How do I find V at the end point? Martin, can you tell me how do I find shear force at point B? Habiba, how do I find shear force at point B? Gabriel, what is shear force at point B? Ephraim, Daniel, Ashwin? Yes, that is, thank you, Gabriel. That is 18 kilonewton, isn't it? So let's check and make sure we got it the same value. So I put x equal to 9. So I have to plug x equal to 9, and that should be equal to 18, right? According to Gabriel. So that is V of B. That is V at x equal to 9. It should be minus 81 divided by 3 plus 9. All right. So that makes this one equal to minus 19 kilonewton. All right. Is that fair? Yeah, minus 18. Correct. Minus 18. Minus 18. Thank you for that. Now, if I have two endpoints, this endpoint is at minus 19, minus 18, sorry. So going from 9 to 18, it should pass, it should intersect with the x-axis, isn't it? So when it intersects, that is going to be a quadratic change. So how do I find that point? This point is very important. I call this x star. So why x star is important? Because the relationship between m and v is derivative. So therefore, when v is 0, m is maximum. I do need to find x star because that is the point at which the bending moment become maximum. All right. So how do I find x star? Daniel Jensen, how do I find x star? Jaden, how do I find x star? Habiba, how do I find x star? That is where v becomes 0, right? So this is v. This is v of x. So let's set v of x equal to 0. So if I, so v of x star, that is equal to 0. It's equal to minus x star squared divided by 3 plus 9. So if I take 9 to the other side, x squared is 27, and then x star is root of 27. So let's find out the value. 5.2. So this is 5.2 meter. All right. So I know that this is the point where shear force becomes 0. All right. How do we go so far? Everyone following the solution? Anyone confused or need more explanation, clarification? Please give me a feedback now. All right. So thank you, Ben. Thank you, Lachlan. Anyone else? If you have concern, if you're confused, just stop me. I'm happy to explain this more for you. And how do we proceed? The procedure is find out. m of x using the differential equation. So that is dm over dx, that is equal to v of x. And v of x is what? V of x is minus x squared 3 plus 9. So let me solve that one and see what do we get. So that is integral of dm is equal to integral of minus x squared 3 plus 9 dx, and that should be simple because the bound of integral are between 0 to x, 0 to x, and this one is minus x cubed divided by 9 plus 9x. And what about the left hand side? The left hand side, that is m of x minus m of a, or m of 0. So what is m of 0? Who can tell me what is m of 0, m of a? Tapiva, what is m of a? Bending moment evaluated at point A. What is it? Daniel? Damien? Damien, do you know what bending moment at point A is? Ben, what is the bending moment at point A? Yes, that is 0, correct? Thank you, Ben. Because this is a pin support, the pin support cannot withstand any bending. So therefore, m of A is equal to m of 0, that is equal to 0. Thank you, Ben, for that. So I'm plugging that one here, that is equal to m of x. This is equal to 0. And the right hand side, that is what? That is the integral which I just solved. All right, now I need to plot that, right? So if I plug x equal to 0, that is equal to 0. And what about the end point? The end point is m of b. So how do I find m of b? Who can tell me how do I find m of b? Martin? Martin Dehani, how do I find m at b? Jaden? Gabriel? Ivan? Ephraim? Daniel? How do I find m at b? Ben? How do I find m at b? Just in this equation, I have to plug x equal to 9, right? Yes. Thank you, Lachlan. Thank you, Lachlan. That integration, I simply plug x equal to 9. That is m of 9. This is equal to minus 9 cubed divided by 9 plus 9 squared. So that is equal to minus 9 squared plus 9 squared, which is 0, right? So the end point is 0. Does this comply with the constraints of the problem? Does it make sense to have 0 bending? Yes, it does, because the end point is a roller support. Roller cannot take bending, and the starting point is a pin. So neither of these two can take a bending, and therefore that makes things very promising. It's a good indication we are in the right track, right? So we are interested in this critical point. So the critical points are at the beginning. At the beginning, I know that is 0. At the end, this is 0. And now I have to find out the middle point, which is at x star. So let's find this at x star. And how do I find m maximum or minimum m star? That is m at x star. And x star, let me check we had this right. Yeah, 5.2, that is correct. I need to plug m at, we identified x star as 5.2, and that is minus 5.2 cubed divided by 9 plus 9 times 5.2. And that, if we solve, that's going to give me 31.2. Is a positive. And the unit is kilonewton meter. And therefore, I can now comfortably, so my bending moment would look like this one. Okay, so that is a cubic function. It has a maximum right at x star, 0 at the beginning, 0 at the end. All right, so conclusions. That is the most important part of the problem. The important part of the problem is um, which part of the beam is most critical? Who can answer this essential question? I mean, which part of the beam is more critical in terms of the loading? So that is why we went through all these mathematics and all these dreadful calculations simply to answer that question. So you have to tell me which part of the beam is most critical. If there is going to be a crack developing in the beam, where does this crack start? 40.5 from the left. So you mean that x star is 5.2? Is that what you mean? I don't know, 4.5. Is that what you mean? Yes, yes, 5.2. But you know, Lachlan, that answer is not 100% correct. This is where the bending is most critical. But from shear perspective, the critical point is point B, isn't it? So are we able to tell which critical point is more critical? Is this the shear point at B is critical? The middle point x star is bending is critical from bending perspective. Which one is more critical? Yvonne, do you know which one of these are more critical, the end point B or the x star 5.2? So let me. All right, how do you know B is more critical? I mean, how do you know B? I would argue that the X star is more critical. So neither of us have any leg to stand. So we are just guessing. All right? And honestly, no one is able to give a precise answer yet. We should be able to answer this question maybe at the end of week 10. All right? At the week 10, we could make a comparison between the critical point due to the shear and critical point due to the bending. So I want to make sure everyone understands this dilemma, this problem we have now. So I want you to be prepared when we are able to answer this question, then you would appreciate it. So does everyone understand what the challenge is? The challenge is the critical point due to the shear, the unit is Newton. The critical point due to the bending, the unit is Newton meter. And the fact is you cannot compare shear and bending because they are different entities. This is like apple and orange. You cannot compare them. All right? Who is with me? All right, thank you, Lachlan. Anyone else? Tapiva, thank you, Tapiva. Thank you, Ivan. Good boys. All right. If anyone doesn't understand, thank you, Martin. If you don't, that's okay, Zoo. Make sure you watch the recorded. If anyone is confused, if they want a clarification, this is the time. Please ask me now. Otherwise, I assume that you are following the class. All right, all we good? Let's move on. Thank you for being such a wonderful audience. And now we move on to something. Um, yeah, these are the solutions, these are the summaries, and these are the equations, right? So the key equation for starting from w of x, deriving v of x, and deriving m of x. These are the key equations. So um, we just started with something very simple. Why this one is discontinuous? Because we do have a point load in the middle, and the w of x is 0, so integral of the 0 is constant. All right, so now let's try this problem here. Here I have a beam which is fitted to the wall. So I think that's a good exercise for everyone. Try to give this a go. I think I'm going to give you 5 minutes for this one. And then we just look at your solutions and take it from there. All right. So let's get it started. Okay, first thing first, let me just label that one. This is point A. This is point A. That's fitted to the wall. This is point B. Okay. And here we want to have W of X, V of X, and M of X. And eventually, what is the critical V and what is the critical M? So I give you 5 minutes, and in 5 minutes, we try this together. So while you're doing that, let me complete the attendance. And Just bear with me. I'm doing the attendance. I'll be with you shortly. Okay. So far, so good. I will be with you now. Yeah. Efraim, in this question, we want to plot the variation of the shear force and bending moment. So we start from finding the variation of the distributed load. That's what we do. All right, let's get started. I think some of you might have solved this problem to some extent or completed it. Let's start with W of X. So who can tell me what is the expression for W of X? Why would you say X? Is this a linear variation or this is a constant one? Ben? Yes, that's constant. And is this positive 500 or minus 500, Ben? Minus. Well done. So that is minus 500. Everyone can follow this. This is a downward distributed load 500. And we know that W of X, the unit is Newton per meter. So that is minus 500. All right. So how do I find everything else? First thing first, I have to find the reactions. So to find the reactions, this is a cantilever. The cantilever, I want to draw the free body diagram. That is A of X, sorry, A of Y. A of X is 0. And what about the bending moment? The bending moment, that is M of A. So how do I find M of A? Well, first thing, I need to replace that distributed load with a constant load. That is the area under this one. That is minus 500 times 2, which is 1000, right? 1000 Newton down, minus. So this is minus 1000 Newton. And therefore, AY becomes 1000 Newton. And then MA is 1000 times half of this distance, which is 1. So MA is 1000 times 1, which is 1000 Newton meter. All right. So that is MA. Now that I have these solutions, so let me just make some space. So that is V of A. V of A, that is V at x equal to 0 is equal to 1000 Newton. All right. And what about M of A? M of A is, yeah, M of A is um, 1000. Is this positive or is this negative? That is negative, right? So that is minus Newton meter. So now I can start integrating from W of X. So dV over dx, that is W of X, is minus 500. And therefore, integral of dV between 0 to x is integral of minus 500 dx between 0 to x. And that is V of x minus V of 0. is equal to minus 500x. Okay, so that is v of 0 is what? V of 0 is 1000. All right, that is v of a. So therefore, my expression for v of x becomes, so I take this one to the right hand side, that is minus 500x plus 1000. Okay, I can test this one. At the starting point, v of 0 is 1000. And what about v at the end point? V of b, that is v at x equal to 2, that is minus 500 times 2 plus 1000, which is equal to 0, right? So the end value is 0. How does v changes? The v variations is a line with a negative slope. So I think we are ready to plot the variation of v of x with x. So the starting point is 1000 Newton and the end point is 0, right? So, and then how does it change? Linearly changes between. So we managed to plot v of x, a prime, and versus x. This is the first part of the question. So the second part is we have to find out the variation of the bending moment. So bending moment, how do we do bending moment? That is another integration. So let me see if you have the access to the solution for this problem. Yeah. All right. So how does it work for m? Again, the equation we start with, that is d of m over d of x, that is equal to v of x, which is equal to minus 500x plus 1000. And if I solve this integral, that gives me integral of dm between 0 to x is equal to integral of this guy over here. So that the integral is minus 500 divided by 2x squared plus 1000x, and that should change between x and 0. So now this one is m of x minus m of 0. So m of 0 is m of a. All right. And right hand side, that is minus 250 x squared plus 1000 x. And I think this one, we have a positive bending moment here. Or, sorry, that is negative. Yeah, that is negative. And now minus minus is positive. So that is m of x plus 1000 equal to that. 1000, I take it to the left hand side. That is m of x is equal to minus 250 x squared plus 1000 x minus 1000. That is the expression I have for bending moment. All right. Who can tell me how do I find the bending moment at the starting point? So m of a, that is m with x equal to 0, that is minus 1000 Newton meter. And how do I find the end value of bending? So that is m at point B, which is m at x equal to 2. So x equal to 2, let's find out what that is. That is minus 2,252 squared plus 1,000 times 2 minus 1,000. So that is 4, this is minus 1,000 plus 2,000 minus 1,000. So the end value m of b is equal to 0. So is this making sense? Is that what you expected? Do you expect it to have the find value equal to 0? Just have a look at this problem. Does this make sense? Yes or no? Yes, that is correct. Well done, Ben. Uh, anyone doesn't follow? Yep, Lachlan, thank you for that. So now we have two values of the end values of the bending moment, and we are one step closer to plotting the variations, aren't we? Okay, so now I start from the starting point, which is minus 1,000, and the end value is 0. So that equation is a quadratic equation. A quadratic equation with a negative um, multiplier of the largest term, that means a reverse cup. So this is a reverse cup, a quadratic, and that should go like this, right? And so between the shear force, there is no zero. So the zero value is here. Therefore, I can expect this is the maximum point. This is the maximum point. How do I know the slope here is horizontal? Because this is the maximum point. And how do I know this is maximum point? Because shear is 0 here. So I think now we managed to plot the variations, and now this is the conclusion time. So critical point for the v of x, the critical point is v star is equal to v of a. And what is the critical point for the bending moment? Zoo, can you tell us what is the critical? Ephraim, what is the critical point for the bending moment? M of x. So this is M of x, Ephraim. Can you point out where the critical point is? Jaden, what is the critical bending moment? The largest value. Just look at the variations. Ephraim, this is a bending graph. I mean, I did the graph. So you have the variation of M of x with respect to the x. So which number has the largest absolute value, Ephraim? Just make an educated guess. Toss a coin. Gabriel, which point is critical for bending moment? Liding, Martin, Matt Abidur, which point is critical for bending? Don, Ashwin, Ashen, anyone home? Isn't that obvious? I did the plot m of x versus x, and all you have to answer is by looking into this variation. Yes, thank you, Lachlan. Thank you, Khan. Why you say middle, Khan? So yes, Martin is correct. A is critical because that has the largest absolute value. I mean, Correct, this is the negative value, but if the beam is deformed, the beam doesn't care if you bend it upward or downward, it's going to break, right? So as long as the deformation is large, it is more critical. So Martin is correct, Lachlan is correct. The critical point is point A. So critical bending, that is M at A. So does that make sense, Ephraim? Khan, does that make sense? All right, thank you very much. Khan, what about you? All right, thank you, thank you. All right, this was a simple problem, and this only had one zone of the loading. No change of the loading in between. You only have to plot this between A and B. If the status of the loading was changing, we needed to consider multiple zones, and this is not the case here. All right, so let's go to one more. Okay, the next topic is relatively simple to do, but a little bit difficult to understand. And for that reason, I want everyone to be listening well. This is a very important concept I want to introduce to you. All right, so are you ready? All right, so this is the problem. You go to a bonding shop, and here you buy a section, a timber. So this timber is 2 by 5, and this is the first configuration. And in the second configuration, you decide to place your beam like so. So the length is the same, the supports are the same. The only difference is you decide to put this one in a tall configuration, configuration 1. This one you place that in a configuration, so still that is 5, 2, and let's assume that this is 10 meter, this is again 10 meter, and that is configuration 2. Now I have a quiz for you, a question, and that might be, all right. So here you purchase this one $10. This one is $10, and here you have say 50 kilonewton here, and here you have 50 kilonewton here. So everything is the same. The only difference is you want to decide whether to utilize that in a tall position or in the flat position. So I'm just expecting everyone to answer this question. Whether your answer is correct or not, this is not relevant, but I want to hear what you have to say. Okay, so far I have correct answers from Ben, Damien, Igor, Ivan, Lachlan, and these are all the correct questions I have. And I expect Ashen, Ashwin, Don, Daniel, Ephraim, Jack White, Lyding, Nat, and Zoo to cast their answers. All right. So now I have correct answer from Don. No, not Don. Ben, Damien, Daniel, Igor, Ivan, Jaden, Khan, Lachlan. These are all the correct answers I have. All right. So before I tell you the answer, yeah, all right. Now I have answer from Lai as well, but still, what about Ashen? What about Ashwin? Are you there? Maybe not. So the correct answer is one. Configuration one is stronger. And if you wonder why, I ask you to do a very simple experiment. So wherever you are sitting, I think you might find a ruler next to you, right? So a ruler is very comparable to this timber. I mean, doesn't matter if that's made of steel or if that's plastic or if that's wooden, doesn't matter. So I want you to hold the ruler between your finger and try to bend it in the tall configuration and then try to bend it into flat configuration. So the same ruler, nothing has changed, same force, same supporting points, but then you find this much easier to bend when you are try to bend it in this configuration. That is much easier to bend, isn't it? This one, you won't be able to bend it at all. I mean, would break or you would injure your fingers. If you try to bend it that way, this is much, much stronger in that configuration. So no surprise that if you are constructing a building, so you have a wall here, and then you prefer to put your timber in a tall configuration rather than the flat configuration. Flat configuration, it easily bends, but if you put it into the tall one, it would resist much better. Does that make sense to everyone now? I mean, forget about all mathematics. Imagine you don't know anything about the mechanics of a structure. So you can visualize that the ruler won't bend into the tall configuration, but it bends into the flat configuration easier. All right, so everyone understand that. And now, can you explain to me that why is this the case? Why the same material, same price? I mean, you didn't change anything. Simply you rotated that 90-degree. What happens here? Why one configuration better than the other? Anyone has an explanation? If you do, I'm happy to give you one bonus mark for the exam. All right, I'll be surprised if anyone can explain, but yeah, the question was, do you have any explanation why the very same structure, the very same ruler is a stronger? Okay, Lachlan mentions this is area. This is close, Lachlan, but not quite the answer. The direction of action. Well, Lachlan was closer. Lachlan mentioned this has something to do with the section property. When I say section property, so section, no, not thickness, not thickness, section property. So section property, yes. Let me explain. There are three section property or geometrical property. One is area. One is CG, center of area. The other one is moment of inertia, second moment of inertia. And you remember that either IXX or IYY. So this is axis X, this is axis Y. So if you remember from energy and motion, this is IXX, this is IYY. So for the very same geometry, IXX is 1 over 12 BH3. So this is B times 5 cubed. and the other configuration that is 1 over 12, 5 times 3 cubed. So this one is larger, isn't it? That is 1, this is 2. So I1 is much larger than I2, isn't it? Because this is 5 to the power of 3, this is 3 to the power of 3. So if you calculate that, you find out that this is the second moment of inertia. Second moment of inertia, you have this in the energy and motion. And then here you have your very first um, understanding of the performance of the structure. Performance of the structure is not only a matter of the load, so this is the load, is not the um, limited to the weight. I mean, both configuration, the same weight of the material, the same length, same material. Also, it depends on some section properties. In this case, it depends on the moment of inertia. All right? I'm telling you, the larger the moment of inertia, the stronger the structure. Okay? So just take this as a recipe. From now on, if I give you a section, you want to know its moment of inertia, because moment of inertia, I mean, this is a comparison between two identical things. So what if I want to make a comparison between two non-identical shapes? So imagine Lachlan, Ben, or everyone else. I ask you, look, I have to you have to choose between these two sections for the very same problem. So this is my problem. So this one is $2, that's the price. This one is maybe $1. So which one you choose? It has nothing to do with the dollar. So load is the same, distance between the things are the same. So if you want to make a choice between them, yes, the rectangle is stronger, and you go for this one. Why? Because you just by looking at this one, the moment of inertia for rectangle is larger than moment of inertia for the circle, right? So that is the one you choose for your structure. So whatever we said so far, I want you to just try to understand. It is super critical to calculate moment of inertia. Why moment of inertia is important? Because it is a key performance parameter for a structure. So the larger the moment of inertia, the stronger the structure is, irrespective of anything else to the structure. From now on, we want to find out how to calculate the moment of inertia. And you know what? There are two avenues for that. One avenue is painful, one avenue is comfortable. So the painful is by integration. So you can find out the moment of inertia by integration, and that is the definition. This is a painful. So what is the comfortable way of calculating moment of inertia? That is using the table, right? So you as engineers, you have access to the engineering tables. In the exam, you have access to the formula sheets. So you don't have to calculate the moment of inertia for a rectangle. You don't have to calculate it for a circle, because in the table you will be provided with a formula to find them. The question is how to use the table. And you know what? Even using the table is not straightforward. You might think using table is for dumb people. It is not. Even if you want to use a table, you have to have some basic understanding of what comes from the table that is a standard value. You may need the non-standard value. So let me explain for you what it means. So let's go back to the very same example I showed you here. This is a circular, this is a rectangular cross section. All right. So with this rectangular cross section, I want to consider two configurations. The first configuration is I decide to, so these are two identical. You purchase this from the Bunning and you decide to either rest them against their edge or you want to rest them against this middle point. So how can you do it? This is not an issue. I mean, you can drill a hole past the shaft or so here in these two configurations, that is configuration 1, this is configuration 2. So both of them, this is 5, this is 2, 5, 2, but the moment of inertia for 2 and moment of inertia for 1, they are not equal. All right. Do you know why? So when you look into the lookup table, the lookup table would give you something like that. I equal to BH 1 over 12 BH3. No, that's not the correct answer. So here the bending is done with respect to the center of gravity. So this is called the standard. This is the standard I with respect to the CG. The non-standard is this one. This is non-standard. You have it with respect to one edge. So that is now I choose my coordinate system, not right in the middle. I choose my coordinate system here. And in this case, I is 1/3 of BH3. So have a comparison between them. Which one is largest? This one is largest, isn't it? Right? So how do I go from here to there? That is called the theorem of parallel axis. The theorem of parallel axis. You had this in energy and motion. Then you were told that the I1 is equal to I2 plus a penalty. So you go to the standard table, pick the standard value, but your case is not a standard. Your case is non-standard. So you are resting this against its edge. So there is a distance here. The distance is called b. So the penalty is b squared times the area. So this is the area of the beam. So you have to add a penalty to the standard table to get the non-standard value. This is called the parallel axis theorem. Parallel axis theorem. So this is how you modify a value from the formula sheet. If the value you are after to calculate is not standard, is not with respect to the center of the area, you have to pay a penalty. The penalty is the square distance of the distance between two multiplied by the area. All right. Who wants me to explain this again? Anyone who followed the explanation, please give me a feedback. All right, let me explain again. Thank you, Ben. Thank you, Ben. Thank you, Lachlan. Anyone else? I would explain that again. So here I have a situation for you. So this situation is I have a rectangular section, and in the first case, yeah. So let me. There is no correct or wrong. I mean, for some reason, you have to uh, have different access. And let me explain that to you. So in one instance, you have your coordinate system right in the centroid of the section. And in another configuration, you have your coordinate system not at the center, but at a different position. But the thing is, the distance between these two are d. So this is a standard, and by integration, by mathematical derivation, dh, ph, and this is the area. All right. So here, by integration, you find out that the I for case 1, this is case 2. I for case 1, that is 1 over 12. B, this is H. All right. So here you find out the standard moment of inertia with respect to this axis. This is XX. 1 over 12 BH cubed. But for this one, if you do the integration, your moment of inertia is 1 over third BH3. So the question is, how do you go from this standard value to non-standard? So you can write it this way. My non-standard moment of inertia is equal to that of a standard plus a penalty. The penalty is d squared. D squared is d squared multiplied by area. So that is the theorem of parallel axis. So these two axes are parallel, this one and this one are parallel. That means in the exam, you have access to this formula sheet, but for some reason, I tell you what that reason is later, but for some reason, you only have access to this one from the formula sheet. You have to modify that formula to get this formula. How do you do it? All you need to know is the standard value, the distance between two parallel axes, and the area that this is being shifted. So if you follow that equation, this is to customize your specific moment of inertia, not to be identical with that of the standard. All right. Does that make sense? Can I have some of your feedback, please? Anyone wants to be explained again, please ask me. I'm happy to explain it again. No, the area doesn't change. The area doesn't change. Thank you, Khan. Thank you, Igor. Thank you, Ivan. Thank you, Lachlan. Thank you, Ben. All right. So all we did so far, I wanted you to understand the importance of the section properties. You might ask yourself, why on earth, why on hell should we calculate area? Why should we find the center of area? Why should we find the moment of inertia? And here I'm telling you why. I think knowing why makes the experience less painful. Look, we are all in it. That's a very painful situation, all mathematics. But if we are not blindfolded, if we know why we are doing this, maybe the pain can be taken easier. All right. Thank you for being patient. So here I have situation for you. We have a rectangular section, and as I mentioned, this is BH. The moment of inertia with respect to the centroid, that is a standard. This is the standard. 1 over 12 BH3. Or here this is called D, that is H. All right? And if I have my x-axis or x prime axis, x prime here, that becomes I x prime, and this is I x plus half of this distance, which is h by 2 multiplied by the area. And if you simplify that, after simplification, what you get is 1/3 BH3. That is after simplification. So this was a simple example where we can see the difference between a standard moment of inertia and non-standard. So also we find out the parallel axis theorem. So yeah, let's go to um, yeah. So and that explains why if you rotate this 90 degrees, one of them is much larger. Which one is largest? I think the one which has d in it square. This is larger. Ixx is larger than Iyy. So this is a tall configuration. This is a flat configuration. All right, let's do that for triangle. I mean, you can go through the painful channel by integrating, starting from the first principle formula, that is the definition of I. So if I integrate that one, after doing the integration simplification, the final answer is for a triangle with a horizontal side of B and vertical side of H, the moment of inertia with respect to the centroid. This is a standard again. Standard, that is my x-axis is passing through the CG. So that is the definition of a standard. If you ask me what a standard is, a standard is when the x-axis or the bending axis passes through the center of area. Okay? So for the standard moment of inertia, that is 1 over 36 BH cube. So BH cube makes that comparable to the rectangular section, but this coefficient make that different. So this is much smaller than 1 over 12, isn't it? This is 1/3. So you can make a comparison. A triangle is weaker than that of the identical rectangular section. Okay, that makes sense. Now, we could do the same thing, I mean, here with the parallel axis theorem. If I decide to bring my x-axis here, x prime, x prime, and this makes that non-standard. So now my I x prime, x prime, that is I xx plus a penalty. The penalty is the distance between these two, d squared multiplied by the area of this one. This is area. That is how to go from standard into non-standard. Parallel axis theorem. Now we do the same thing for the circle, the circular cross section. And the important thing is not how to derive it. The important thing is the final answer. The final answer is 1 over 4 pi radius to the power of 4, or 1 over 64 pi diameter to the power of 4. That is for the full circle. And again, guess what? This is CG. That is a standard. If you wanted non-standard, so you need to know this distance, which is the radius. You need to know this is area, and this is x prime, x prime. So I x prime is I xx plus d squared a. That is the penalty term. So in the exam, you will be provided with the standard value. And for some reason, if you don't need the standard one, you need the non-standard one. That is how you can cook it for yourself. Okay, so far, does that make sense? Thank you, Igor, Ivan, Lachlan, Ben. Thank you, everyone else. Let's summarize the result. These are, that is a standard. This is a standard. This is a standard. Why they are a standard? Because they are passing through the CG. What if I need that of the non-standard? Let it be here, let it be there, or let it be here. All I need is the distance between these two parallel axes, and I need the area. So this is B. So then I can put my own moment of inertia with respect to any desired plane of bending. All right. So also in the formula sheet in the exam, you will be provided the moment of inertia for half circle, quarter circle, and a half circle in which the coordinate axis is with a distance at the some other places. So in a sense, this is not a standard, is it? Because this is not through the center of area. I mean, whatever you are provided in the exam, in a formula sheet that is a standard, and what you want, if that is different with that one, that makes it non-standard. And to go from a standard to non-standard, all you need is the distance between two parallel axes. So if you have the distance between two parallel axes and you have the area, you can cook your own moment of inertia. All right, so that is the parallel axis theorem, and now it should be easy for you to understand, isn't it? And this slide is when you put a summation that has a meaning. So why there is a summation? Because a shape could be primitive or it could be compound. So what is a compound shape? What is a primitive shape? So let me ask this question by running a simple quiz. All right, can I get everyone answering this question, please? Which shape is compound? All right, now I have correct answers from Ben, from Yvonne, from, yeah, these correct. The correct answers are from Ben and Yvonne. So correct answer: Ashwin correct, Ben correct, Igor correct, Yvonne correct. All other answers you have to think twice. Ashwin correct, Ben correct, Damien correct, Igor correct, Yvonne correct. These are all correct answers we have so far. What about Gabriel? What about Jack? What about Matt Abidur, Nat, Zoo, Ashen? So Ashwin correct, Ben correct, Damien, Igor, Yvonne, Lachlan, all correct. All right. Now, the notion of, thank you for everyone. The correct answer is A. The correct answer is A. A is a compound, and I tell you why. I tell you why this is compound, and just watch this one. So here, this is a compound. So with the compound, what it means is this is a circle, this is a rectangle, right? So I say I compound is equal to I of the rectangle minus I of circle. So why is this minus? Because here we have removed, we have drilled a hole inside a positive area. So this is the positive, this is negative. So that is a subtractive nature. And so a compound is not always like that. So this is also a compound. So this is a compound. So here I compound is I of 1 plus I of 2. So I look into the table, that is the I find for the first shape. So I can break this one into two shapes. In this case, both shapes are positive, so that is positive, positive. In this shape, one shape is positive, one shape is negative, so the total I is this minus that. So if you ask why can we add the values together, the justification is moment of inertia. Is this a vector value or a scalar value? Is this a numeric or is this a vector value? Yes, thank you, Ivan. That is a scalar. Scalars, we can add them together easily, like numbers. 2 plus 2 is 4. But vectors, we cannot add them easily. So a vector of 2, another vector of 2, the sum does not necessarily mean 4. So something like moment of inertia, because the nature of the moment of inertia is a scalar. Scalars can be added together. So here we have two scalar value. I of the sorry, this is a triangle. I should have said triangle. Triangle. So I of triangle minus I of the circle. Here, I of the first rectangle plus I of the second rectangle, both of them positive. All right. So I think that is the most. So here I have a compound shape. This compound shape, how many primitive shapes are here? How many primitive shapes? Yes, thank you, Ivan. There are three primitive shapes. Every primitive shapes, you find their corresponding I value from the table. You find them from the formula sheet. And then you have to do a cooking. That cooking involves using the table formula sheet, using the parallel access theorem, and also you have to use the compound principle which I mentioned to you. So first, you have to break that into several primitive shapes. For every primitive shape, you get the standard values from the table, and then to mix them together, there is a problem here. Who can tell me how can we mix them properly? What is wrong? Why can't we use the standard formula? What is wrong with adding the standard formula together? So, if you can answer this question, well done. Yes. Different orientation. And what about the center of area, Ben? So, yes, all answers are correct, but let me clarify this. So, you refer to the formula sheet, and according to the formula sheet, a standard means that is either here or that edge, depending how the formula is given. You have the I value measured with respect to this point or this point. For that shape, you find the bending reference. A standard is either here or a standard is here. For this shape number 3, the standard value has a center here or center here. But with this compound shape, where is the center of area? The center of area is the red point, right? So remember, we did that before. For a shape like this, how do I find the center of area? The center of area, I call this y bar, measured from here. So y bar is equal to, this is number 1, this is number 2, this is number 3, according to E1. So that is y bar number 1 times area of 1 plus y bar of 2 is multiplied by area of 2 plus y bar of 3 area of 3 divided by a1 plus a2 plus a3, right? So now there is a problem. For the compound shape, the center of area is here. When I bring the values from the formula sheet, it's either here or it's here or it's here. But don't panic, because in either of the cases we can find this is as a D1, this one is D2, and this one is D3. And this one is A3, this one is A2, and this is the area of 1. So for every individual value from the table, I can find out the penalty. The penalty for the first shape, second shape, third shape. For this one, the penalty is D1 squared A1. The penalty for this one is d2 squared a2, and the penalty for the third shape is d3 squared a3. So you mix these values with those you grab them from table, and here you are. You cooked your dinner. You cooked your lunch. Okay. Does who followed my explanation or analogy? Thank you, Ben. Thank you, Igor. Thank you, Ivan. What about you, Lachlan? What about everyone? Thank you, Lachlan. What about Zu, Lai, Tapiwa, Jack, Gabriel, Ephraim, Igor, Daniel, Damien, Ashwin, Ashen? So do you want me to explain again? If you do, you have to let me. Okay, thank you, Lighting. All right, it's good to have some feedback. At least I know that I'm not talking to myself. But please, if anyone is confused, if anyone needs explanation, the professional thing, the decent thing is to ask me. Right here, I'm begging you to ask me for clarification. Later on, if you complain, that is just an excuse, right? So don't be that who just, yeah, you know what I mean. All right, here we have the um, animated solution. So I want to find out the moment of inertia for a compound shape. So that compound shape, first I start with a reference point. My reference point is the x-axis at the bottom. Could be somewhere else. And then before I proceed, I want to bring your attention that the way you decompose a compound shape into the primitive shape is not unique. You can do this in a different ways, right? So you can do this in a different ways. For example, if I have a shape like this, I can write this as a rectangle plus a triangle. That is one solution. The other solution is I make a large triangle like so, say a large triangle minus a tiny shape here, right? So this is also true. So all I'm saying is a compound shape doesn't have a unique decomposition. There are different ways you can decompose this one, but as usual, we prefer to be the smart guy. The smart guy is that who chooses the easiest scenario. You know what I mean? So let's see how this one does. We take the bottom line as a reference. First thing first, I have to find out the centroid of this compound shape, and that is easy. So I find the everything with respect to the centroid of this shape. So the centroid, I have already calculated this as 118.95 millimeter, and these are for the compound shape. I have to break that into three pieces. Number one, number two, number three. So now I highlight the first shape, that is the first calculation, area number one. So that has a centroid of primitive shape as 10 millimeter, and then that makes the distance between the centroid of the first shape with that of the entire compound shape is 108.95, right? Sorry, one, yeah, 118 minus 10, yeah. This is the penalty, that is the penalty. This is the one you get from the table, this is a standard value. And that penalty added to this one is the moment of inertia of the yellow with respect to the centroid of the compound shape. So this one we finished. Let's go to the next one. The next one is I make the middle one as area number two. So area number two, that is again standard plus the penalty, and finally we do that for the third shape. For the third shape, and all we have to do is we add them together. So how do we add them? This is I1, primitive 1, primitive 2, primitive 3. And this is simply because these are scalar values. The scalars, you can add them together easily. Okay? All right. Now, that is your turn. Can I ask everyone to tell me how do you go for this example? I give you 3 minutes. In 3 minutes, you just tell me how this can be done. Um, Ashen, did you resolve that crack issue? Did you talk to Greg? Has he got back to you yet? Ashen? Hello, Ashen. Are you there? Can you hear me? You are not? Okay, almost 3 minutes over. So, this is a very sweet problem. Why this is sweet? Why this is easy? Because the compound shape is equal to I of the rectangle minus I of circle, right? And what is interesting, what makes this problem simple is both rectangle and circle, they have their center of gravity coincided with that of the formula sheet. That means for this problem, no parallel access theorem. So that makes this problem simple, right? So you find this one from the standard formula sheet, this one from the standard formula sheet, and just subtract that of the circle from that of rectangle. That is your answer. No need for penalty for correction. Okay? And then we have this one, and that brings today lectures to end. So in summary, what we did today, we summarized the method of equation. Method of equation is very important. You always have to start from um, the finding reactions, developing an expression for distributed load as a function of x, and then to integration, applying the boundary condition. Of course, you need to know how many loading zones are there, whether there are discontinuity, whether there are point loads or just distributed. And then we went through a number of practices. And secondly, we realized that the performance of a beam structure is not only relying on the load or geometry, also it relies on the second moment of inertia. Moment of inertia is very important. Somehow it is time consuming to calculate, but the good news is if you understand it, You know that in exam you definitely have to do the calculation, right? So something you can't miss it, you can't afford to miss it, but as long as you know how to do it, is something doable, something comparing to most to other most complex topics is straightforward. You know how to calculate this one. All it takes is to calculate the centroid of a compound shape, decompose it into primitive shapes, and then writing a scalar decomposition equation. And that brings today's class to its end. If you have any question, I'm happy to take your question now. Ashen, can you hear me? If you do, just give me a yell. I have a word with you. All right, thanks very much. I look forward to see you soon. Thanks very much. Thank you, Igor. Thank you, Ben. Thanks everyone for being wonderful listener. Thanks, Ivan. Thank you, Lighting. Thanks, Ephraim. Ashwin, are you there? Ashwin, can you hear me?